Hi guys, I'm Nachika and I'm attempting Blackpenredpen's Golden Buzzer Challenge of 101 integrals in one take. I've got the questions right here with me and let's get started. So we have the integral of tan to the fifth power of x secant cubed x dx. You can rewrite this as integral of tan to the fourth power x secant squared x secant x tan x, which can be written as then you can use a substitution of u is equal to secant x, and this right here is equal to du, and we'll have integral of u squared minus 1 squared times u squared du, and expanding the bracket gives u to the u squared is u squared whole squared is 4 times u squared, which is u to the 6, minus 2 u to the power 4 minus plus u squared du, and integrating that gives 1/7 u to the 7 minus 2/5 u to the 5th plus 1/3 u to the 3rd plus c, which is equal to 1/7 secant to the power 7 of x minus 2/5 secant to the power 5th of x plus 1/3 secant cubed of x plus c. For question number 2, we have the integral of cosine 2x over sine x plus cosine x dx. To solve this integral, we need to use the double angle identity, and you can rewrite this as cosine squared x minus sine squared x over sine x plus cosine x dx. You can cos squared minus sine squared can be written as cosine x plus sine x times cosine x minus sine x, and you can simplify the fraction, and we need to integrate cosine x minus sine x dx, which is equal to sine x plus cosine x plus c. Question number 3. This is the integral of x squared plus 1 over x to the power 4th minus x squared plus 1 dx. You can integrate this question using first you can divide everything by x squared, so you get 1 plus 1 over x squared over x squared minus 1 plus 1 over x squared dx, and you can rewrite that as 1 plus 1 over x squared over you can complete the square here to give x minus 1 over x whole squared, and the constant over here is -2, but here we have -1, so you just have to add 1. Now you can perform a u substitution here with where u is equal to x minus 1 over x, and therefore du is equal to 1 plus 1 over x squared dx, which gives that as our du. So you can rewrite this integral as integral of du over u squared plus 1, and this is a standard integral of arctan of u plus c, which is arctan of x minus 1 over x plus c. For the next question, we have the integral of x plus e to the x all squared dx. This can be expanded as x squared plus 2x e to the x plus e to the 2x dx. And you can apply power rule to integrate the first term, which is 1/3 x cubed. And for the middle term here, we need to use integration by parts. And so I'm doing that here using the DI setup. I will differentiate 2x and I will integrate e to the x. The integral of e to the x is always e to the x. The derivative of 2x is 2, and that gives 0. That's e to the x. Therefore, this integral the integral of 2x e to the x can be given by 2x e to the x minus 2 e to the x. And the final integral here, you can reverse the chain rule, so we get e to the 2x and 1/2, reversing the chain rule, plus c. Question number 5, we have the integral of cosecant cubed of x, secant x dx. This can be rewritten in terms of sine and cosine, and we have 1 over sine cubed of x cosine x dx, and 1 can be written as sine squared x plus cosine squared x. And using the identity, we can split up the fraction into sine squared x over sine cubed x cosine x dx plus the integral of cos squared x dx over sine cubed x cosine x. Simplifying this, we get 1 over sine x cosine x, and on this side we have cosine x over sine cubed of x. This can be integrated just by using a u substitution with u is equal to sine x, because then cosine x dx will be du. Over here we have 1, which again we can write as sine squared x plus cosine squared x using the identity, which gives us the integral of sine squared x over sine x cos x dx plus the integral of cos squared x dx over sine x cosine x plus the integral of cosine x dx over sine cubed of x. Simplify this down, we get sine x over cosine x, which is integral of tangent x. Here we get integral of cosine x over sine x, and now we can evaluate all of these integrals. For the first integral you can use, this is the integral of tangent x dx, and using a u substitution of u is equal to cosine x, this evaluates to natural log absolute value of secant x. Then we have the integral, then here we use a u substitution of u is equal to sine x, and we have an integral of du over u, and here again we use another u substitution of u is equal to sine x, and that gives us an integral of u cubed du. So the second part of this integral can be evaluated as the natural log absolute value of u, which is sine x, and this can be, you can integrate this using the power rule here, which gives an integral which when integrated gives u to the power of minus 2 and times 1 over 2, and expanding that and substituting u back in gives negative sine x to the power of minus 2 over 2, and don't forget the plus c. It's 5 done, 95 more to go. Number 6, we have the integral of cosine x over sine squared x minus 5 sine x minus 6 dx. We can use a u substitution where u is equal to sine x, du is equal to cosine x dx, so that we have 1 over, and this this expression in terms of sine here you can be factorized, and it gives u minus 3. You have u minus 6 times u plus 1, and yes, that's the term, and we can then use partial fractions to split this up. So we have a over u minus 6 plus b over u plus 1 dx, so du, and when you set u is equal to 6, this term right here is equal to 0, so you get a, so we get 7a is equal to 1, so we have a is equal to 1 over 7, with u is equal to minus 1. We have the term with a equal to 0, and we get minus 7b is equal to 1, so we get b is equal to minus 1 over 7. Using that, we can then rewrite this as 1 over 7 integral of 1 over u minus 6 plus du minus the integral of minus 1 over 7, the integral of 1 over u plus 1 du. And as you can see, these are linear terms, so you can rewrite this using this integrates to a natural log term, and that gives 1/7 natural log absolute value of u minus 6, where u is sine x. So substituting that back in, we have sine x minus 6, and minus 1 over 7 natural log absolute value of sine x plus 1 plus c. And since we have the same terms here, you can factorize the 1 over 7 and rewrite this as ln absolute value sine x minus 6 minus natural log sine x plus 1 plus c. And using natural log properties, you can rewrite this as a single quotient, giving you natural log absolute value of sine x minus 6 over sine x plus 1 plus c, which is our final answer. Then we have question number 7, which is the integral of 1 over square root of e to the x dx. You can rewrite this as the integral of e to the minus x over 2 dx using the index rules, and the integral of e to the x is e to the x, and then we can reverse the chain rule, which gives us the integral for e to the minus x over 2 as e to the minus x over 2 multiplied by minus 2. Yes, and that is correct. And we have plus c. Question number 8, we have the integral of e to the x square root of e to the x minus 1 over e to the x plus 3. You can use a u substitution here, where u is equal to square root of e to the x minus 1, u squared is equal to e to the x minus 1. We have 2u du is equal to e to the x dx, and we have our e to the x dx. So you can rewrite this integral as the integral of u du, and e to the x plus 3 can be written as u squared plus 4. Now to integrate this, we can integrate this, you can multiply the numerator and denominator by 2, and then you can perform a u substitution where, let's say, 2u du yes, so now we can have let m equal to u squared plus 4, and taking derivative with both sides, we have dm is equal to 2u du, and you can therefore rewrite this as 1 over 2 integral of dm 1 over m, and this is just the natural log, so we have 1/2 natural log of absolute value u squared plus 4 plus c, and u squared plus 4 is indeed e to the x plus 3. Then for question number 9, we have the integral of 1 over x plus square root of x dx, and to solve this integral you can perform the u substitution. U is equal to square root of x, u squared is equal to x, and we have 2 u du is equal to dx. Performing the substitution, we get 2u du over x is u squared, so we have u squared plus u, and now over here, if we had a 2u plus 1, then that would match. Then we can perform a u substitution with for u squared plus u, where we only have 2u. So what you can do is you can say 2 times u plus 1. No. So you can rewrite this as 2u plus 1 minus 1, and see, then you can split up the integral into 2u plus 1 du over u squared plus u minus the integral of 1 over u squared plus u du. This integral, the first integral, evaluates to a natural log situation, and you have natural log absolute value of u squared plus u. And for the second integral, you have 1 over u. You can factorize the denominator as 1 over u times u plus 1 du. Applying partial fractions, we can have the integral of a over u plus b over u plus 1. Setting u is equal to 0, we have a is equal to 1, and setting u equal to minus 1, we get b is equal, so we get minus b is equal to minus 1. And this therefore allows us to compute these integrals as so these integrals, when evaluated, result in negative natural log absolute value of u plus natural log absolute value of u plus 1, and writing all of that back in, we have negative natural log absolute value u, positive natural log absolute value of u plus 1. And since we can then combine all of these to give natural log absolute value of u squared plus u over u plus natural log of u plus 1 and substituting u back in, we get x plus square root of x over square root of x, which then simplifies to square root of x plus 1. And here we have square root of x plus 1 as well. And you can then rewrite this entire integral as natural log absolute value square root of x plus 1 whole squared plus c, or twice the natural log of square root of x squared plus 1 plus c. For the 10th integral, we have integral from minus 1 to 5, absolute value of x minus 3 dx. And you can evaluate this algebraically by splitting up the integral, or you can sketch a graph and calculate the area. Sketching the graph of absolute value of x minus 3, we have y is equal to absolute value of x minus 3, where this point is x equal to 3. At x equals 5, y is equal to 2. At x equals minus 1, y is equal to 4. So we need the sum of the area of these two triangles. The area for the first triangle can be given by half times the base, which is between minus 1 to 3 you have 4, so half times 4, and the height, which is 4, plus the area of the second triangle, which is half times the base, which is 2, times the height, which is also 2. And we then have this, which evaluates to 8 plus 2, which is 10. Question number 11, we have the integral sine x over secant to the power of 2019 x dx, and you can rewrite this as the integral of cosine, since 1 over secant is cosine x, cosine to the power of 2019 x sine x dx. And now we can perform a u substitution where u is equal to cosine x, du is equal to minus sine x dx. So therefore this integral evaluates to negative integral of u to the power of 2019 du, and using the integral for the power rule, we have minus u to the 2020 over 2020 plus c, and substituting u back in, we have minus cosine x to the power of 2020. For question 12, we have the integral of x sine inverse of x over square root of 1 minus x squared dx. So one thing to notice is 1 over square root of 1 minus x squared is the derivative of sine inverse of x. So it's useful to perform a u substitution here with u equal to sine inverse of x, and we have du is equal to 1 over square root of 1 minus x squared dx. So all of this right here is du, and substituting this back in So performing the substitution, we get x is equal to sine u. Sine inverse is u, and we have du. And now we can perform this integral using integration by parts, for which I'm using the di setup here. Differentiate u and integrate sine of u. Integrating sine of u gives minus cosine of u. Differentiating u gives 1. Differentiating 1 gives 0. And integrating minus cosine u gives minus sine u. And therefore we have the answer to this integral as minus u cosine u plus sine u plus c. And now substituting back in terms of x, we have u is equal to sine inverse of x, so we have minus sine inverse of x. And for this, with the substitution, we have the following triangle where this is u and cosine u is square root of 1 minus x squared, and sine u is x plus c, which gives us our final answer of square root of 1 minus negative square root of 1 minus x squared multiplied by sine inverse of x plus c. That's it. For question 13, we have the integral of 2 sine x over sine of 2x dx, and you can perform this integral by expanding sine of 2x. We know that using the double angle identity, sine of 2x is equal to 2 sine x cosine x. And simplifying using this identity, this integral reduces to the integral of 1 over cosine x dx, which is the same as the integral of secant x. To calculate this integral, we multiply the numerator and denominator by secant x plus tan x. And expanding the numerator, we get secant squared x plus secant x tan x. Now you can notice that if you perform the substitution that the denominator is equal to u, we get all of the numerator equal to du. This is because the derivative of secant x is secant x tan x, and the derivative of tan x is secant squared x, and therefore this simply reduces to the natural log situation, and we get the natural log absolute value of secant x plus tan x plus c. For question number 14, we have the integral of cosine squared of 2x dx. Now to calculate this integral, we need to use the power reduction formula for sine. Power reduction formula for cosine. Cosine squared x can be written as 1/2 plus 1/2 plus cosine of 2 theta over 2, and in this case theta is equal to 2x, and we have 2 times 2x, so we have 4x for the cosine, and dx. Now integrating, integral of 1/2 dx is x over 2, and the integral of cosine is positive sign, but remember, since we have the cosine of 4x, we need to reverse the chain rule, and reversing the chain rule, we need to divide by 4. So we need to divide by 4, and we already have a 2 in the denominator, so that gives us the final answer as sine of 4x over 8. And we have our final answer of x over 2 plus sine of 4x over 8 plus c. Question number 15. We now have the integral of um, 1 over x cubed plus 1 dx. To perform this integral, we need to factorize the denominator, which can be factorized as x plus 1 times x squared minus x plus 1. And therefore we can then perform partial fractions. So we have the integral of a over x plus 1 plus bx plus c over x squared minus x plus 1 dx. So now, performing partial fractions, we take the value of x is equal to minus 1 to get the entire second half of the partial fraction equal to 0, and that gives us a times minus 1 squared is 1 minus 1, 0. So we get a is equal to 1. So we have the value a is equal to 1. Now using the substitution for x is equal to 0, we now get the equation a plus c is equal to 1, and since a is equal to 1, we get c is equal, and since we have a is equal to 1, we get c is equal to 0. And finally, performing a substitution of x is equal to 1, we have this part right here equal to 2, so we have 2b plus 2 times c, but c is 0, so we have nothing there, and we have 2b plus a is equal to 1, and since a is equal to positive 1, we get oh, I've made a mistake here, sorry. At x equals minus 1, we get a times minus 1 squared, which is 1, plus 1, plus 1, so we have 3. So we have 3a is equal to 1, so we have a is equal to 1/3. Therefore, for x equals 0, we have a plus c is equal to 1, so we then get the value for c being 2/3. And finally, for x is equal to 1, we perform substitution and we get 2b plus 4/3 plus 1 plus 1 minus 1, which is 1 plus 1/3 is equal to 1. And therefore we get the values for 2b is equal to 3 over 5. Oh, sorry. We get 2b is equal to 1 minus 5 over 3. And we have b, which is equal to 3 minus 5 over 3. We have minus 2/3, and we have b is equal to minus 1/3. this now allows us to calculate this integral, and the first part of the integral is 1/3 natural log absolute value of x plus 1, and you can have that because this is just a linear term here, and you can split up, and for the second part of the integral you can factorize to 2/3. We have the integral of x minus 1 over x squared minus x plus 1 dx. Now here we can perform a u substitution with the denominator being u, and we get, if the denominator is u, we get 2x minus 1 is equal to 2x minus 1 dx is equal to du, and to get that final, so making the substitution, we get, so we need 2x minus 1, so you can rewrite this as 1/3 times 2 times x minus 1. Because you have the x minus 1, this when expanded gives you 2x minus 2, but we need 2x minus 1, so you can add a plus 1 here, and you'll get 1/3 natural log absolute value of x plus 1 minus 1/3 natural log absolute value of x squared minus x plus 1, and we have the final integral to evaluate, which is minus 1/3 integral of 1 over x squared minus x plus 1 dx. You can complete the square here to rewrite this as x minus 1/2 squared, and the constant term here is positive 1 over 3, but here you need plus 1, so you can add you can add 3 over 4, and 3 over 4 can be written as square root of 3 over 4. 3 over 4 can be written as the square root of 3 over 2 all squared, and therefore we can evaluate this integral as an arctangent. So we get our final answer as 1/3 natural log absolute value of x plus 1, and simplifying this natural log terms as x plus 1 over x squared minus x plus 1, and we have minus 1/3, and since we have square root of 3 over 2 here, we need to divide by that, so we have 2 over square root of 3 arctan of x minus 1/2 divided by square root of 3 over 2, so multiplied by 2 over square root of 3 plus c, and continuing this to simplify the answer further. Continuing where we left off from here, we have this being equal to 1/3 natural log absolute value of x plus 1 over x squared minus x plus 1, and minus 2 over 3 root 3 tangent inverse of 2 over root 3x 2 over root 3x minus 1 over root 3 plus c. So that was question 15. Moving on, we have question number 16, which is the integral of x sine squared x dx. So you can use we have to use a power reduction formula here, and we can rewrite sine squared of x as 1/2 minus cosine 2x over 2, and therefore this integral can be written as the integral of x over 2 minus x cosine of 2x over 2 dx. And the first term is linear, and we can then use the power rule to integrate that. For the second term, we have to use integration by parts. I'll be differentiating x over 2 and integrating cosine of 2x. Differentiating x over 2, we get positive 1/2. Integrating cosine of 2x, we get 1/2 sine of 2x. And differentiating 1/2, we get 0. Integrating 1/2 sine of 2x, we get minus cosine of 2x over 4. Now, simplify, and now evaluating the integral, the first part evaluates to x squared over 4, and yes, that's correct. And for the second part, we have a minus sign here, and our answer is x over 2 times 1/2 sine of 2x, so we have x sine of 2x over 4, and multiply that by the positive minus minus becomes plus, and we have cosine of 2x over 8. And therefore, distributing the minus, we have x squared over 4 minus x sine 2x over 4 minus cosine 2x over 8, and don't forget the plus c. That's question 16 done. We have question 17, which is the integral of x plus 1 over x squared dx, and expanding out, we get x squared plus 2 plus x to the minus 2 dx, and you can integrate this using the power rule. We have 1/3 x cubed plus 2x minus 1 over x plus c, and that's done. Now we have question number 18, which is the integral of 3 over x squared plus 4x plus 29 dx. And we can take out the 3, and completing the square in the denominator we get x plus 2 whole squared, and here we get the constant term for 4, but here we have 29, so you can rewrite this as 5 squared dx, and we can take a u substitution for u is equal to x plus 2, du is equal to dx, and you can see that we have the arctangent situation here. So evaluating this integral we get 3, and since we have a 5 here we have to divide by 5, so 3 times 1 over 5 arctan of x plus 2 over 5 plus c, and you can just clean up the fraction as 3 over 5, and that's it. Question number 19, we have the integral of cotangent to the 5th power of x dx. For this question we will be using the identity 1 plus cotangent squared x is equal to cosecant squared x, and using this identity we can rewrite cotangent as 1 as cosecant squared x minus 1, which is cotangent squared. Squaring that gives us cotangent to the power 4 multiplied by cotangent of x dx. And expanding the bracket and distributing the cotangent, we get cosecant to the 4th power of x cotangent of x minus 2 cosecant minus 2 cosecant squared x cotangent x plus 1 times the cotangent x dx. And now what you can see is that you can take out 1 cosecant from each term, and you can have cosecant cubed x, cosecant x, cotangent x. Here you'll have cosecant x times cosecant x, cotangent x, and here you just have cotangent x. Now if you notice, you can perform a u substitution with u is equal to cosecant x, because the derivative of cosecant is negative cosecant x cotangent x. So therefore we can split up this integral as the integral of cosecant cubed of x, cosecant x cotangent x dx, minus 2 times the integral of cosecant x cotangent x, plus the integral of cotangent x, which is just cosine x over sine x. Now, performing the u substitution here, we have, I forgot dx here, but this is our du, and this is u to the power 3. So we have minus du, We have this as our minus du, and this is u, and integrating we get minus from here, and the integral of u, and we have the integral of u cubed, and that is just 1/4 u to the power 4, which is cosecant to the power 4x. Over here we have minus becoming plus, integral of 2 times 1/2 u squared, so we get just u squared, which is cosecant squared x, and we have the final part of our integral here, which is just a natural log situation where you substitute q is equal to sine x, and your cosine x dx is the du here. So this part of the final part of the integral evaluates to natural log absolute value of sine x, and don't forget the plus c. Now we have question number 20, which is the integral from -1 to 1 of tan x over x to the 4 minus x squared plus 1 dx. Now, without looking at this, without calculating this integral, you can just say that this is equal to 0. That's because tan x is an odd function, and the polynomial at the bottom is an even function because we have even powers of x, and an odd function divided by an even function is equal to an odd function. And since an odd function is symmetric around the origin, the integral from -1 to 1 for an odd function is equal to 0. That's 20 questions done. We have 18 more to go. We're 1/5 of the way there. Moving ahead, we have question number 21, which is the integral of sine cubed of x cosine squared x dx. Now, since cosine and sine go together, and as sine is the derivative of cosine, what we can do here is we can rewrite this integral as the integral of sine squared x cos squared x times sine of x dx. And as you all know, sine squared can be written as 1 minus cos squared x. Therefore, performing the substitution with u is equal to cosine x, we get du is equal to minus sine x dx, which then gives us negative integral of 1 minus u squared times u squared du, and we therefore need to integrate u to the power 4 minus u squared du, and we have 1/5 u to the power 5, where u is cosine x, so we have cosine to the 5th power of x, minus 1/3 cosine to the 3rd power of x plus c. And that's the answer for that one. So I think it's been about 1 hour since we began. That's just the first page done. Question number 22. The integral of 1 over x squared square root of x squared plus 1 dx. We can use trig sub over here where x is equal to tan u. So x is equal to tan theta, dx is equal to secant squared theta d theta, and this integral simplifies to 1 over tan squared theta. Tan squared plus 1 is secant squared, square root of secant squared is just secant theta, and dx is secant squared theta d theta. And now we have the integral of cosine squared theta over sine squared theta and multiplied by secant theta d theta. And now we can perform, so we lose the power here on the top, and now we can perform a u substitution where u is equal to sine theta, and cosine theta d theta will be du. So we now have integral of 1 over u squared du, which then evaluates to minus 1 over u plus c. And since u is sine theta, and we have to substitute this back in terms of x, so we have x is equal to tan theta, and therefore the hypotenuse is 1 plus x squared, which then gives me the value that I need for 1 minus 1 over sine theta plus c. Sine theta is x over square root of 1 plus x squared, and the reciprocal of that is square root of 1 plus x squared over x, and that's it. Next we have question number 23, which is the integral of sine x, secant x, tangent x dx. And to evaluate this, I'm going to write everything in terms of sine and cosine. We have the integral of sine squared x over cos squared x dx. Now we can rewrite sine as 1 minus cos squared x, and therefore we can split this integral up, and we get the integral of 1 over cos squared x dx minus the integral of dx, and this is just the integral of secant squared theta, and the derivative of tan theta is secant squared, so we have tan x for the first integral, and we just have minus x plus c, and we're done. Now for question number 24, we have the integral of secant cubed of x dx. Now to do this, I'm going to split this up as the integral of secant squared x times secant x dx. I'm going to use the identity secant squared is equal to tan squared x plus 1, which then gives us the integral of tan squared x secant x, tan squared x secant x plus secant x plus c, plus times dx, and now once again, to evaluate the integral of tan squared secant x, I will be using the identity tan squared is equal to secant squared x minus 1, and that will give me, so just rewriting this integral, we have the integral of secant x dx from here, plus the integral of secant cubed of x minus the integral dx minus the integral, no, ignore that, so here we have the integral of secant x dx plus the integral of tan squared x secant x dx. And now we can use integration by parts here. We'll be integrating secant x tan x and differentiating tan x. The derivative of tan x is secant squared x, and the integral of secant x tan x is just secant x, and therefore we have the integral of secant x dx plus, so we know the integral of secant x dx, which is natural log absolute value of secant x plus tan x, and then we have plus secant x tan x, and then we have minus the integral of secant cubed x dx. And now, as you can see, all of this is equal to integral of secant cubed of x. So sending this over to the other side, we'll have 2 times the integral of secant cubed x dx is equal to natural log absolute value of secant x plus tangent of x plus secant x tan x, and then dividing both sides by 2, we have this integral is equal to 1/2 natural log of secant x tan x plus 1/2 secant x tan x plus c, and that's it. Now we have the integral of, now we have question number 25, which is the integral of 1 over x square root of 9x squared minus 1 dx. We can perform a trig substitution here, and the substitution I'm going to perform is that 9x squared is equal to 9x squared is equal to secant squared x, and performing this substitution we have x squared is equal to 1 over 9 secant squared x, and we have 2x dx. Oh, sorry, secant squared of theta. So yeah, we have 1/9 2 secant theta, and the derivative of secant is obviously secant theta tangent theta d theta. And performing the substitution, we get 1/x and 1/x and square root of secant squared theta minus 1, and dx is equal to 1/9, and the 2 just cancels out, so we have 1/9 secant squared theta tan theta d theta all over x here. And if you'd notice, you'll see that we have 1/9 so if you notice carefully, you'll see we have the integral of 1/9x times x, which is 9x squared, so we can rewrite that as secant squared theta, which gets rid of the x's. The square root of secant squared minus 1 is just tan theta, and on the top here we have secant squared theta tan theta d theta, and all of that simplifies to the integral of 1, which is just theta plus c, and substituting x back in, we can have so the substitution we made was secant squared is equal to 9x squared, therefore secant theta, which is secant theta is equal to 3x, and therefore theta is equal to secant inverse of 3x, because secant theta is 3x, and yes, and we have the plus c. That was question number 25. Now we move on to question number 26, which is the integral of cosine square root of x dx. Performing a u substitution for u is equal to square root of x, we get u squared is equal to x, and we have 2u du is equal to dx. We have the integral of cosine u times 2u du, and now we can perform integration by parts here. So with the di setup, I'll be differentiating 2u and integrating cosine of u. Derivative of 2u is 2, and then it's 0. Integrating cosine gives sine of u, and which is negative cosine of u, and then we have the answer to this integral, which is 2u sine of u, and minus is plus 2 cosine of u plus c, and substituting u back in, we have substituting u is equal to square root of x, we have 2 square root of x sine of square root of x, and 2 cosine of square root of x. And that's our answer. Moving on to question number 27, we have the integral of cosecant x dx. or rewriting this in terms of sine, we have the integral of 1 over sine of x dx. To perform this integral, I will be expanding the numerator using the trig identity, so I'll have integral of sine squared x over sine x dx plus the integral of cosine squared x over sine x dx. And you can notice that this is just the integral of sine of x, which is minus cosine x dx, minus cosine x. And over here, we have the integral of cosine of x times cotangent of x. How can I calculate that? I think I'll just use integration by parts to calculate this entire integral. So, using integration by parts, I'll integrate 1 and I'll differentiate cosecant of x. The derivative of cosecant is negative cosecant x cotangent x. Integral of 1 is just x. And I have this is equal to x cosecant of x plus minus plus the integral of x cosecant x cotangent x dx. I think my initial approach might have been correct. I think multiply the numerator and denominator with so I have cosecant x here, multiply the numerator and denominator by cotangent of x minus cosecant x and now performing a u substitution with the denominator as u, we have du is equal to negative cosecant squared x, and derivative of cosecant x is negative cosecant x cotangent x, and that minus and minus becomes positive cosecant x cotangent of x dx, and therefore you can rewrite this as integral of du over u, and that's just a simple natural log with absolute value of cotangent of x minus cosecant of x plus c. Moving on to question number 28. We have the integral of square root x squared plus 4x plus 13 dx, and you can complete the square here and rewrite that as x plus 2 whole squared, and the constant term here is 4, but we need 13, so we have an added 3 squared. And now I'm going to perform a u substitution with x plus 2 being equal to 3 x plus 2 is equal to 3 tan theta, and now we have dx is equal to 3 secant squared theta d theta, and therefore this integral is equal to 9 times tan squared theta plus 1 multiplied by 3, and substituting dx we have 3 secant squared theta d theta, and now we have this integral simplifies to 3 times 3 secant to the 4th power theta d theta. To evaluate this integral, I'll be using the identity. I think I'll isolate one secant squared theta d theta, and I have another secant squared theta, which can be rewritten as tan squared theta plus 1 times secant squared theta d theta. Distributing the secant squared, you have tan squared theta secant squared theta plus secant squared theta d theta. Now you can perform a u substitution for the first part of this integral, where u is equal to tan x and the derivative of u is secant squared x. So we have a u squared du plus 9 times the integral of secant squared theta, and the integral of secant squared theta is just tangent of theta. So all of this simplifies to 9 times 1/3 tan cubed theta plus 9 times tan theta, and moving over, continuing on this side of the board, continuing over here, we have 3 tan cubed theta plus 9 tan theta, and now we need to substitute back in terms of x, where tan theta is equal to x plus 2 over 3, therefore we have x plus 2 over 3 cubed plus 9 tan theta is 9 times x plus 2 over 3 plus c. And just to clean up the fraction a bit, we have 3 cubed is 27, and 3 over 27 is 1 over 9, x plus 2 cubed plus, we have 3 times x plus 2 plus c. If you want, you could simplify this a bit and just say this is equal to 3x plus a different constant c2. Moving on to question number 29, we have the integral of e to the 2x cosine of x dx. I'll just be using integration by parts for this. With the di setup, I'll be differentiating e to the 2x and I'll be integrating cosine x. Differentiating e to the 2x is 2e to the 2x, and differentiating that again we have 4e to the 2x. Integrating cosine x we get positive sine x, integrating that we get negative cosine x, and I think I can stop there because I can see this integral re-emerging here. So writing the result of integration by parts, we get e to the 2x times sine of x, and we have minus minus, which is plus 2e to the 2x cosine of x, and we have plus times minus, so we have minus the integral of 4 e to the 2x cosine of x dx. Now you can notice that you can take 4 outside the integral and you have the repeating integral here. So if you push this to the left hand side of the equation, you have 5 times the integral of e to the 2x cosine x dx, and we get that is equal to this part right here, which is e to the 2x sine x plus 2e to the 2x cosine x, and dividing both sides by 5 we get 1/5 on either side, and don't forget the plus c, and that is our answer. So that was question number 29. Now we have question number 30, which is the definite integral from 3 to 5 of x minus 3 to the power 9 dx. Now since the term inside the bracket is linear, you can straight away perform a substitution of u is equal to x minus 3, and we get du is equal to dx, so you can rewrite this limit from x is equal to 3 to x is equal to 5 for u to the power 9 du, and because we have x is equal to 3, we have the value, we can rewrite the limit in terms of u, where we get u is equal to 0, and we get till u is equal to 2. and therefore evaluating this integral we get 1/10 u to the power 10 from 0 to 2, and when you calculate that we get that's 1/10 of 2 to the power 10 minus 0, and that is 1024 over 10, which is 512 over 5, and that's it. Moving on to question 31, we have the integral of 1 over square root of x minus x to the 3 over 2 dx. Now you can take out a square root of x, so we can rewrite this as the square root of x times the square root of x minus x dx. Because if you multiply, this is what you get when you factorize. Oh, sorry. So yes, you can factorize and you can say x times 1 minus square root of x. And then we can perform a u substitution with where u is equal to 1 minus the square root of x, and you get du is equal to minus 1 over 2 root x dx, and we then have the integral of 1 over, splitting up this square root, we have square root of x times square root of 1 minus square root of x, and we know that dx is equal to minus 2 square root of x du, and plugging in u, we get u over here, and as you can see the square root of x just cancels out, and we now have minus 2 integral of u to the power minus half du, and you can integrate this using the power rule. So we have minus 2 times minus half plus 1 is plus half, and dividing by positive half we get multiplying it by 2, and we have u to the power 1/2 plus c, and that is equal to minus 4, and substituting u back in we get the square root of 1 minus square root of x plus c, and that's the answer. Moving on to question number 32, we have the integral from 1 over the square root of x minus x squared dx. To calculate this integral, you can once again factorize an x, and we have 1 minus x dx, which is equal to the integral of 1 over square root of x times the square root of 1 minus x dx. And now I can perform the substitution for x is equal to sine squared theta. I get dx is equal to 2 sine theta cosine theta d theta, and substituting that I get 1 over square root of x will be sine theta, 1 minus sine squared theta is cosine squared theta, so I get square root of cosine squared theta, which is cosine theta, and dx is equal to 2 sine theta cos theta d theta, and these just cancel out, and the integral of 2d theta is 2 theta plus c, and rewriting theta in terms of x, we have, since x is equal to sine squared theta, square root of x is equal to sine theta, and therefore theta is equal to arc sine of square root of x, and our final answer is 2 arc sine square root of x plus c. Question number 33. We have the integral of e to the 2 ln x dx, which can be rewritten as e to the ln of x squared dx, and since we have the integral of ln of x squared, and this simplifies to the integral of x squared dx, which is simply 1/3 x cubed plus c. And that's the answer for that integral. That's 33 integrals done. We're 1/3 of the way through. It's been about 1 hour and 40 minutes so far. Now we keep going. We're on question 34, which is the integral from integral of natural log of x over square root of x dx. I could perform a u substitution, or I could do integration by parts. I think I'll straight away go to integration by parts. I'll be differentiating natural log of x and integrating x to the minus half. Derivative of natural log of x is 1 over x. Integral of x to the minus half is 2x to the half. And therefore this integral can be written as 2, sorry I miswrote that, this integral can be written as 2 times square root of x natural log of x minus the integral of 2 square root of x over x dx. And this is just a simple power integral, which is 2 times x to the minus half dx, because square root of x over x is 1 over square root of x, and we have 2 square root of x natural log of x, and the derivative using the power rule for that is minus 2 times 2 square root of x plus c, and just the 2 times 2 is 4, and that is the answer. Now we have question 35. Question number 35, which is the integral of 1 over e to the x plus e to the minus x dx. I think you can how can I do this? So this integral is 1 over e to the x plus 1 over e to the x, which is the integral of 1 over e to the x squared plus 1 times e to the x dx, because this e to the x in the denominator, by making a common denominator, goes on the top there. E to the x whole squared. And now we can perform a u substitution with u is equal to e to the x, du is equal to e to the x dx, and we therefore have the integral of du and 1 over u squared plus 1, and as you can see, this is just the classic arctangent scenario. So we have this integral evaluates to the inverse tangent of u, which is e to the x, inverse tangent of e to the x plus c. Now on to question number 36. We have the integral of log base 2 of x dx. This can be rewritten as, using the change of base rule, we get natural log of x over natural log of 2 dx, and natural log of 2 is a constant, so you can take that out, and to integrate natural log of x you can do integration by parts. So performing the di setup here, I'll be differentiating ln of x and integrating 1. The integral of 1 is x, derivative of natural log of x is 1 over x, and therefore I have my answer as this integral of natural log of x dx evaluates to x ln of x minus the integral of x over x dx, which is the integral of 1 dx, and this is equal to x ln x over natural log of 2, and the integral of 1 is just x, so we have minus x over natural log of 2 plus c, and if you natural log of x over natural log of 2 can be rewritten as x log base 2 of x log base 2 of x, minus x over natural log of 2 plus c, and that's the answer. Question number 37 is the integral of x cubed sine of 2x dx. I think I will straight away perform integration by parts on this. So di set up here, plus, minus. So I will be differentiating x cubed and integrating sine of 2x. So the derivative of x cubed is 3x squared. Differentiating that we have 6x, differentiating that we have 6, and differentiating that again we have 0. Integral of sine of 2x is minus cosine of 2x over 2. Integral of that is minus sine of 2x over 4. The integral of that is plus cosine of 2x over 8, and the integral of that is sine of 2x over 16. And now, to get our answer, we have to multiply that with that and add up all of those products. So this integral is equal to minus 1/2 x cubed cosine 2x, and minus is plus 3 over 4 x squared sine of 2x. Then we have plus and plus, so we have plus 6 over 8, which is 3 over 4 x cosine of 2x, and we have a minus plus, which is a minus 6 over 16, which is 3 over 8 sine of 2x, and don't forget the plus c, and that's the answer for that question. Now we have question number 38, which is the integral of x squared cube root of 1 plus x cubed dx. You can perform a simple u substitution here with let u equals 1 plus x cubed, du is equal to 3 x squared dx, and therefore continuing from that, we have the integral of x squared times u to the power 1/3, and dx is equal to du over 3x squared, and the x squareds cancel, and that integral evaluates to 1/3 times 1/3 u to and the integral of u to the power 1/3. 1/3 plus 1 is 4/3, and dividing by 4/3 is the same as multiplying by 3/4. And we have u to the power 4/3 plus c, and that is equal to 1/4 1 plus x cubed to the power of 4/3 plus c. Moving on, we have the integral. We have question number 39, which is the integral of (1 over x squared plus 4 all squared dx). Now I'm going to perform a new substitution here with x squared is equal to, no, I think I'll make the substitution that x is equal to 2 tan theta, dx is equal to 2 secant squared theta d theta. Now, this integral is equal to 1 over x squared is 4 tan squared theta. 4 tan squared theta plus 4 is the same as 4 secant squared theta, and everything squared, and dx is equal to 2 secant squared theta d theta. This is equal to the integral from 2 sec squared theta over 16 secant to the 4th power of theta d theta, and we have the integral of 1 over 8 1 over secant squared theta d theta, and 1 over secant squared is the same as cosine squared theta d theta. Now we can just apply the power reduction formula for the cosine, and this term is equal to 1/2 plus cosine of 2 theta over 2. Therefore, we then have 1/8, and we get integrating 1/2 is theta over 2. So yes, and cosine of 2 theta, the integral for that is sine of 2 theta, and however you're undoing the chain rule, so you have to divide by 2, so you have 1/2 times 1/2, which is 4, and now we need to substitute back in terms of x. So we had the triangle with tan theta being equal to x over 2. So we have the hypotenuse as x squared, square root of x squared plus 4. And obviously you can rewrite this as theta over 16 plus, using the double angle identity for sine, we have 2 sine theta cosine theta, and we have 8 times 4, which is 32, and continuing up here, theta is equal to arctan of so tan inverse of x over 2, so we have 1 over 16 tan tan inverse of x over 2, and we have plus 1 over 16, and sine of theta is x over square root of x squared plus 4, x over square root of x squared plus 4, and cosine theta is 2 over square root of x squared plus 4, and all of this just simplifies to 1 over 16 tan inverse of x over 2 plus 1 over 8 x over x squared plus 4 and plus c. That's the answer. Question number 40. We have question number 40. The integral from 1 to 2 square root of x squared minus 1 dx. So there are several ways to do this integral. So there are several ways to do this integral. You can either do this with the trig sub, setting x is equal to secant theta. Another way of doing this is by identifying that this is the area under the hyperbolic function. So with the hyperbola, which has this has the equation y squared. This has the equation y is equal to the positive square root of x squared minus 1, and this is 1. And we want the integral from 1 to x is equal to 2. And the area under this curve, which is this, is given by the area of this triangle minus, not the area of this portion so this coordinate here, so if this area is t over 2, the coordinate here is hyperbolic cosine of t and hyperbolic sine of t, and therefore we know that the area we need under this curve is the area of the red triangle, which is half times base, which is 2, times the height, which is square root of 4 minus 1, which is square root of 3, minus t over 2, and t over 2 can be, because of the relationship between the hyperbola and the hyperbolic trigonometric functions, this can be written as square root of 3 minus 1/2 the inverse of hyperbolic cosine of of 2, or square root of 3 minus 1/2 inverse of hyperbolic sine of square root of 3. So both of these give the answer. However, you can also perform the trig substitution, and I'm going to do that here as well. So to do the trig substitution, you need to use a substitution x is equal to secant theta, and you have dx is equal to secant theta tan theta d theta, and now we have the integral from x is equal to 1 to x is equal to 2. And we have square root of secant squared minus 1, which is square root of tan squared, so we have tan theta times secant theta tan theta d theta. So now we have a tan squared term here, and you can rewrite that as secant squared theta minus 1, and multiply that by secant theta d theta. And we know the integral of secant cubed, so this gives us two integrals, the integrals of secant cubed and the integral of secant, both of which we know from the previous question. So the integral of secant cubed is 1/2 secant theta tan theta plus 1/2 natural log absolute value secant theta plus tan theta, and the integral and the negative integral of secant x here is minus natural log absolute value secant theta plus tan theta. And you'll notice that you can just simplify this by changing the positive, because these two terms add up to negative 1/2 absolute value, negative 1/2 natural log absolute value of secant theta plus tan theta. And this has to be evaluated between x is equal to 2 and x is equal to 1. And if you substitute this back, if you substitute x back in, you'll have 1/2 x, and tan theta is square root of x squared minus 1, and you'll have the natural log of absolute value of secant theta, which is x, plus tan theta, which is square root of x squared minus 1. And then evaluating the integral this integral at from x is equal to 2 to x is equal to 1, we have 1/2 x, which is 2, times root 3, minus 1/2 natural log absolute value of 2 plus root 3, minus 1/2 times 1 times 0, plus 1/2 natural log absolute value of 1 plus 0. And natural log of 1 evaluates to 0. This term is 0, and therefore we have root 3 minus 1/2 natural log absolute value of 2 plus root 3. So those are 3 different ways to calculate this one integral. 2 of them using hyperbolic trig functions and 1 using a trig substitution. Now we have question number 41. This is the integral of hyperbolic sine of x dx. To calculate this integral, what you need to do is this integral is equal to the hyperbolic cosine of x plus c, and this can be shown using the very definition of the hyperbolic function. Because hyperbolic sine is e to the x minus e to the minus x over 2, this is the very definition of the function. Integrating you can split up the fraction into 2 halves, so you have the integral of e to the x over 2 dx minus plus the integral of minus e to the minus x over 2 dx, and this is equal to e to the x over 2 plus e to the minus x over 2, reversing the chain rule, plus c, and this right here is the definition for Yeah, sorry about that. I'm using the phone to record the audio and it just stopped recording for a second. So yeah, I've just reset that now. So yes, this is the very definition of cosine of h, and that's why this integral is the integral of hyperbolic sine of x is equal to hyperbolic cosine of x. Question number 42. We have the integral of hyperbolic sine squared of x dx, and using the definition of the function you can expand this integral out as e to the 2x, so 1/2 e to the 2x minus 2 plus e to the minus 2x dx, and this is equal to 1/2. The integral of e to the 2x is 1/2 e to the 2x, reversing the chain rule. Integral of minus 2 is minus 2x, and the integral of e to the minus 2x, reversing the chain rule, we have minus 1/2 e to the minus 2x. And all of that evaluates to so yes, I'm just going to clear the rest of the board so I have more space to work on. So yes, this, you can see that this is clearly 1/2 of e to the 2x minus e to the minus 2x over 2 minus 2x. And what you might be able to recognize here, that this indeed is 1/2 hyperbolic sine of 2x minus 2x, and that is equal to hyperbolic sine of 2x over 2 minus x. Oh yeah, don't forget the plus c. And what we've done here is we've found a power reduction formula for hyperbolic sine squared of x. Question 43. We have the integral of hyperbolic sine cubed of x dx. So we can use the hyperbolic identity here. So the functions that define the hyperbolic sine and cosine have the identity of x squared minus y squared is equal to 1, and the x coordinates can be represented by hyperbolic cosine squared of t minus, and the y coordinate is the hyperbolic sine squared of t, and this is equal to 1. So we can use this identity to evaluate this integral. So this integral can be written as integral of hyperbolic sine squared of x, and we have hyperbolic sine of x dx, and hyperbolic sine squared of x can be given by cosine squared. This is given by hyperbolic cosine squared of x minus 1, and therefore this integral now becomes the integral of hyperbolic cosine squared of x sine hyperbolic x dx minus the integral of hyperbolic sine of x dx. Now we can use the u substitution here. So derivative of hyperbolic cosine of x is equal to hyperbolic sine of x, and therefore we can perform a u substitution where we take u is equal to hyperbolic cosine of x, and we have an integral of u squared du, and over here on this side we just have the integral seen in question number 41 there, which evaluates to negative hyperbolic cosine of x plus c, and evaluating this integral here we get by applying the power rule we get 1/3 u to the power 3, which is a hyperbolic cosine to the power of 3 of x minus cosine hyperbolic x plus c. And that's the answer for question 43. And that's the second page completed. Now we have question 44, which is the integral of 1 over square root of x squared plus 1 dx. Now, just how we have hyperbolic trigonometric functions, the derivative of the inverse of hyperbolic sine of x is equal to 1 over square root of x squared plus 1, and so therefore this is a standard integral which is equal to the inverse hyperbolic sine of x plus c. Next up, question 45. The integral of natural log absolute value x plus square root of 1 plus x squared dx. So, as seen in the previous question, we had the integral equal to the inverse hyperbolic sine of x. Now, actually, the inverse hyperbolic sine of x is defined as natural log of x plus square root of 1 plus x squared dx. And since that's the case, we need to evaluate the integral of hyperbolic sine of x dx, and we can do this using integration by parts, using the di method. We integrate 1 and differentiate the hyperbolic sine of x. Integrating 1 gives x, and the derivative of inverse hyperbolic sine is 1 over square root of x squared plus 1. Therefore, we can say that this integral is equal to x inverse hyperbolic sine of x minus the integral of x dx over square root of x squared plus 1. And we can perform a u substitution where x squared plus 1 is equal to u. So we have du is equal to 2x dx, and substituting that we get x inverse hyperbolic sine of x minus the integral of 1 over 2 square root of u du. And continuing work on this side, that is equal to x hyperbolic sine inverse of x, and this is u to the power minus half, and when that is integrated we get negative 1/2, and integral of u to the power minus half is u to the power 1/2, and divided by 1/2 is the same thing as multiplying by 2, so which is equal, and all of this is equal to the square root of u, which is x squared plus 1. And don't forget the plus c. Next we have question number 46, which is the integral of hyperbolic tan of x dx. Now hyperbolic tan x is defined as hyperbolic sine of x over hyperbolic cosine of x, and as now we can perform a u substitution, and we let u is equal to hyperbolic cosine of x du is equal to hyperbolic sine of x dx, and this integral then therefore simplifies to 1 over u du, which is the natural log of absolute value of u, which is hyperbolic cosine of x plus c. Now I have question number 47. This is the integral of hyperbolic secant of x dx. And this is equal to 1 over hyperbolic cosine of x dx. And we can use the hyperbolic identity over here, where we know that 1 is equal to hyperbolic cosine squared of x minus hyperbolic sine squared of x. And this identity allows us to split up this integral, and the resulting integral is the integral of hyperbolic cosine squared over hyperbolic cosine is the integral of hyperbolic cosine of x, then subtracted dx, and subtract from that the integral of hyperbolic sine squared of x over hyperbolic cosine of x dx. And the integral of hyperbolic cosine is, as seen before, is the hyperbolic sine of x. And another way of rewriting this integral is the integral of hyperbolic secant of x multiplied by hyperbolic tangent of x dx. Now, the derivative of hyperbolic secant of x, the derivative of hyperbolic secant x is equal to minus hyperbolic secant of x hyperbolic tangent of x, which is this exact integral, which means that the second integral is a standard integral, giving us the final answer is hyperbolic sine of x plus, since there's a minus on both places, plus the hyperbolic secant of x and plus c. And that was question number 47. Continuing, now we have question number 48, which is the integral of the inverse hyperbolic tangent of x. We can perform this integral using integration by parts. Well, we'll integrate 1 and differentiate inverse hyperbolic tangent of x. So the integral of 1 is x. The derivative of inverse hyperbolic tan is given by 1 over 1 minus x squared. Therefore, this integral becomes x inverse hyperbolic tan x minus the integral of x over 1 minus x squared dx. Now we can perform a simple u substitution here with u being equal to 1 minus x squared, and we have du is equal to minus 2x dx, and plugging that back in, we have, which is equal to x tan inverse hyperbolic tangent of x, and we have minus integral of x over u, and dx is du over minus 2x. And you can see that the x and the x cancel out, and the minus becomes plus, and so you have x inverse hyperbolic tangent over x plus 1/2, and the integral of 1 over u is the natural log absolute value of u, and in this case u is 1 minus x squared and plus c. That's the answer to that question. Next we have question number 49. which is the integral of square root of hyperbolic tangent of x dx. I'm going to take a u substitution here, with u being equal to the square root of hyperbolic tangent of x. Therefore, u squared is equal to hyperbolic tangent of x, and we'll have 2u du being equal to the derivative of the hyperbolic tangent, which is hyperbolic secant squared x dx. Therefore, substituting this back into the integral, we have the integral of u, and we have dx is equal to 2u du over hyperbolic secant squared x. Now we have the hyperbolic identity where secant, we have the identity 1 minus hyperbolic tan squared x is equal to hyperbolic secant squared x, and we can perform this substitution in there, allowing me to rewrite that as 1 minus u to the power of 4. So we have the integral of 2u squared over 1 minus u to the 4 du. I can rewrite this as the integral of 2u over 1 minus u squared whole squared times u du. Now, the derivative of inverse hyperbolic cotangent of x is equal to 1 over 1 minus x squared. Using the chain rule here and reversing the chain rule, I can see that I can integrate this part of the function. Therefore, I can now use integration by parts, where I'll be integrating 2u over 1 minus u to the 4, and I'll be differentiating u. Differentiating u gives me 1, and integral of this is inverse hyperbolic cotangent of x. Therefore, this integral is equal to cotangent, inverse hyperbolic cotangent of u inverse hyperbolic cotangent of u minus the integral of inverse hyperbolic cotangent of u du. And by definition, inverse hyperbolic cotangent of u is equal to 1 over 2 natural log of x plus 1 over x minus 1. Now I think this just overcomplicates this more. I'm just going to change that and try something else instead. So I can I can factorize the denominator as 1 plus u squared times 1 minus u squared, and therefore and I have u squared plus u squared on top. If I could add 1 and subtract 1, then I have the integral of u squared plus 1 over 1 plus u squared du plus the integral of u squared minus 1 over 1 minus u squared du. And this is the integral of 1, which is just u, and over here I have the integral of minus 1. Oh, 1 second. Minus 1 over 1. I can multiply the numerator and denominator by minus 1. So I can have a minus here and a minus outside. And that gives me negative the integral of 1 minus u squared over which is equal to u minus u. Yeah, I've just made a stupid mistake. So yes, I have the integral of u squared plus 1 over 1 plus u squared times 1 minus u squared plus the du plus the integral of u squared minus 1 over 1 plus u squared times 1 minus u squared, and I can eliminate the numerator and part of the denominator here, and I have the integral of 1 over 1 minus u squared du, and over here I can multiply the numerator and denominator. I can change this plus to a minus and multiply the numerator by minus 1, which is 1 minus u squared, over 1 plus u squared times 1 minus u squared, and that eliminates the other part of the denominator here. This gives integral of 1 over 1 minus u squared du minus the integral of 1 over 1 plus u squared du. This integral leads to arctan of u. This integral leads to the inverse hyperbolic cotangent of u, because the derivative of inverse hyperbolic because the derivative of the inverse hyperbolic cotangent is this, and substituting u back in, we have inverse hyperbolic cotangent of square root of hyperbolic tan x minus tan inverse of square root of hyperbolic tan of x. And that's the final answer for question number 49. Yeah, I was just getting confused for that question a lot, and it took me a while to figure it out, and I made a silly mistake partway through. We have number 50. This is the integral of from 0 to 5 of the floor function of x. So this function is a discontinuous function, and its graph looks like this. So from 1, 2, 3, 4, and 5, we have the function is equal to 0 at 0 and is equal to 0 for all values until 1, except at 1 it's equal to 1, at 2 it's equal to 2, this is 1, this is 2, and so on. We have at 3 it's equal to 3, and at 4 it's equal to 4, and so this is 3 and that is 4. So the integral of the floor function from 0 to 5 is the area under this graph, which is 0 for this section. For this part it's 1 times 1, so that's 1. Here it's 2, it's 3, and for this part it's 4. Therefore, this integral from 0 to 5, floor function of x is equal to 0 plus 1 plus 2 plus 3 plus 4, which is equal to 10. We're halfway through. Have to keep going. Next up we have integral of secant to the 6th power of x dx. This can be rewritten as secant to the 4th power of x times secant squared x dx, which can then be written using the identity tan squared x plus 1. This is equal to secant squared x. Squaring all of this gives secant to the 4th power of x, and multiplying this by secant squared x dx gives that integral. So expanding the binomial and distributing the secant squared x, we have the integral of tan to the 4th power of x secant squared x plus 2 tan squared x secant squared x plus secant squared x dx. At this point we can perform a u substitution using u. Oh, sorry, I missed the. Oh no, that was correct. Dx. At this point we can perform a u substitution with u is equal to tan x u du is equal to secant squared x dx. This simplifies these integrals into u to the power 4 du plus 2 times the integral of u squared du plus the integral of du, which is 1/5 u to the power 5, which is tangent x to the power 5, plus 2 times 1/3 u to u cubed, which is, so that gives 2/3 tangent to the 3rd power of x, and we have integral of du, which is just tan x, and plus c. That was question number 51. Question number 52. We have the integral of 1 over 5x minus 2 to the 4 dx. You can perform a u substitution here. 5x minus 2 is equal to u. 5 du is equal to dx. Oh, sorry. 5 dx is equal to du. This gives the integral of 1 over u to the power 4 du over 5, and this gives 1/5 u to the power 5, and dividing by 5 we have 5, and substituting u back in we get 1 over 25 times So we get 1 over 5 integral of u to the minus 4 du, which is 1 over 5 dividing by minus 4 plus 1 is equal to minus 3. Dividing by minus 3, we have minus 1/3, and u to the minus 3. This is equal to minus 1/15, 5x minus 2 to the power minus 3 plus c. So yeah, I'm halfway through and I've spent, I think it's been around 3 hours so far. Moving on, we have question 53, which is the integral of natural log of 1 plus x squared dx. I'm going to make a u substitution with u being equal to 1 plus x squared, du is equal to 2x dx. Making the substitution gives natural log of u, and dx is equal to du over 2x. And in this case, no, I think I won't. No, I think I won't do that. I'll just try to integrate this by parts. I'll integrate 1, differentiate natural log of 1 plus x squared. Integrating 1 gives x. The derivative of natural log of 1 plus x squared is 1 over 1 plus x squared. And using the chain rule, the derivative of 1 plus x squared is 2x. And that gives this integral being equal to x natural log 1 plus x squared minus the integral of 2x squared over 1 plus x squared dx. This is equal to x natural log of 1 plus x squared minus the integral. So if I had, I'll put in x squared plus 1 plus x squared minus 1. Will that work? think I'll just do long division here and see if that works. So I have a remainder of 2, so I can rewrite that as minus integral of 2 dx, and I had a remainder of minus 2, and minus times minus is plus integral of 2 over 1 plus x squared dx. And this is the arctangent situation right here. So yes, so I get x natural log of 1 plus x squared minus 2x plus 2 arctan x plus c, and that's the answer. Next up I have number 54, which is the integral of 1 over x to the 4 plus x dx. And 1 over x to the 4 x dx. Yeah, 1 over x to the 4 plus x dx. This can be written as 1 over x times x cubed plus 1 dx. I try to make a substitution with u being equal to x cubed plus 1 du is equal to 3x squared dx. So I now have the integral of 1 over x times u, and dx is equal to du over 3x squared, which is equal to integral of du over 3x cubed u, which is integral of 1 over, writing 3x cubed, writing x cubed in terms of u, we have u minus 1 times u du. Yeah, my laptop stopped recording the video, so this is the continuation from where I left off. I can do partial fractions over here, and I can have the integral of a over u plus b over u minus 1, and using u equal to 0, we get that minus a has to equal 1, so a is equal to minus 1. Using u is equal to 1, we get that b is equal to 1, and therefore we can expand this out and have the integral of 1 over u minus 1 minus the du minus the integral of 1 over u du, and both of these have linear terms in the denominator, so you can just use a natural log here. So you'll have 1/3 natural log absolute value of u minus 1 minus 1/3 natural log absolute value of u, and plus c. Now substituting u back into the before substituting x in terms before substituting u, you can simplify this these two log expressions as 1/3 natural log of u minus 1 over u using the log rules, and this is equal to 1/3 natural log of 1 minus 1 over u. And now substituting x back into this equation, we have 1/3 natural log absolute value of 1 minus 1 over x cubed plus 1 plus c, and that's the answer. Or these two are equivalent forms, so you can have natural log absolute value of x cubed over x cubed plus 1 as well. Moving on to question number 55, we now have the integral of 1 minus tan x over 1 plus tan x dx. And this can be written as cosine x minus sine x over cosine x all over cosine x plus sine x over cosine x dx, and these two terms cancel out, and leave me with cosine of x minus sine of x over cosine of x plus sine of x dx. Now you can notice that if you take a u substitution of the denominator, then your numerator and dx is your new du, so this is equal to u, du is equal to minus sine x plus cosine x dx, which is the numerator, and therefore we have a situation with 1 over u which integrates to natural log absolute value of cosine x plus sine x plus c. Question number 56. This is the integral of x secant x tan x dx, and you can see that this part of the function integrates to secant x, so we can use integration by parts here. And using the DI method, we have I'll be differentiating x, integrating secant x tangent x, and this gives me secant x and 1, and this leaves me with x times secant x minus the integral of secant x dx. Now, as shown earlier in the video, the integral of secant x can be you can obtain the integral of secant x by multiplying the numerator and denominator by secant x plus tan x, and you get the natural log absolute value of secant x plus tangent x plus c. Yeah, the black pen is running out now, I think. Next we have question number 57. This is the integral of secant inverse of x dx. You can do this using integration by parts. So, integrating by parts, you can integrate 1 to get x and differentiate secant inverse of x, and the derivative of the inverse secant of x is 1 over x square root of x squared minus 1, and therefore this integral is equal to x secant inverse of x minus the integral of 1 over square root of x squared minus 1 dx. And for this part, and to evaluate this integral, we can perform a trig substitution, and assuming x is equal to secant theta, dx is equal to secant theta tan theta d theta, and that gives x secant inverse of x minus integral of 1 over square root of, so secant squared minus 1 is tan squared, square root of tan squared is tan theta, dx is equal to secant theta tan theta d theta, and these cancel out, and as before we're left with the integral of secant theta, which is natural log absolute value of secant theta plus tan theta and plus c. Next I have question number 58. This is the integral of 1 minus cosine x over 1 plus cosine x dx. So multiplying the numerator and denominator by 1 minus cosine x over 1 minus cosine x gives the integral of 1 minus 2 cosine x plus cosine squared of x all over 1 minus cosine squared of x dx. And 1 minus cosine squared of x is equal to sine squared of x. So this integral is equal to the integral of cosecant squared x dx cosecant squared dx minus the integral of 2 cosine x over sine squared minus 2 times the integral of cosecant x cotangent x dx plus the integral of cosine squared x dx over sine squared x dx. So continuing to evaluate this integral, the derivative of cotangent x is negative cosecant squared x. So therefore, the first part of the integral evaluates to negative cotangent of x. The derivative of cosecant x is negative cosecant x cotangent x. So we have and because we have minus 2 cosecant x cotangent x, this integral evaluates to a plus 2 cosecant x. And finally, the final integral can be written as 1 minus sine squared x over sine squared x dx, and minus cotangent of x plus 2 cosecant x plus the integral of cosecant squared of x minus cosecant squared of x dx minus the integral of dx, and that and the integral of positive cosecant squared of x evaluates to negative cotangent of x, and that, so negative cotangent, we get minus 2 cotangent of x plus 2 cosecant x minus x plus c. And that is the answer. Next we have question number 59, which is the integral of x squared square root of x plus 4 dx. So I'm going to perform a u substitution here, where I will pick x plus 4 is equal to u, dx is equal to du, and we have the integral x squared is equal to u minus 4 squared, and all of this is multiplied by square root of u du. Now, expanding the binomial and distributing the square root of u, we have the integral of we have u squared multiplied by square root of u, so we have u to the power of 5 over 2, so that's u squared square root of u. Then we have minus 8 u square root of u, which is u to the power 3 over 2, and then we have plus 16 square root of u, which is plus 16 u to the power half. And all of these can be integrated using the power rule. Therefore, this gives us u to the power 7 over 2 and 2/7 minus 8 times u to the power 5 over 2, and we have 2/5 plus u to the power 3 over 2, and 16 dividing by 3 over 2 is the same as multiplying by 2 over 3 plus c. Substituting u back in to the final answer, we have 2/7 x plus 4 to the power 7 over 2 minus 16 over 5 x plus 4 to the power 5 over 2 plus 32 over 3 x plus 4 to the power 3 over 2 plus c. And that is the answer. Next, on to question number 60. We have the integral from -1 to 1 of square root of 4 minus x squared dx. You can perform a trig substitution here, where x is equal to 2 sine theta, dx is equal to 2 cosine theta d theta. Therefore, this integral is now evaluated at x equals -1 to x equals 1, and square root of 4 minus x squared. X squared is 4 sine squared theta, therefore 4 minus x squared is the same as 4 cosine squared theta. Dx is equal to 2 cosine theta d theta. We can also change the limit, we can also rewrite these limits in terms of theta. When x is equal to 1, theta is equal to sine inverse of 1 over 2, which is pi over 6, and when x is equal to -1, we have theta is equal to sine inverse of -1/2, which is minus pi over 6. Therefore we have integral from minus pi over 6 to pi over 6 square root of 4 cosine squared theta is 2 cosine theta times 2 cosine theta d theta, and we have 4 integral from minus pi over 6 to pi over 6, and cosine squared theta using the power reduction formula is equal to 1/2 plus cosine of 2 theta over 2 d theta, and all of this is equal to 4 times theta over 2 plus sine of 2 theta, and reversing the chain rule we have sine of 2 theta over 4, and this is evaluated from minus pi over 6 to pi over 6, which is equal to 4 times pi over 6 over 2 is pi over 12, sine of pi over 3 is sine of pi over 3 is root 3 over 2, and multiply that by 4, minus, then we have minus of minus pi over 6 over 2, which is minus pi over 12. Then we have sine of minus pi over 3, which is minus root 3 over 2 times 4. And all of this is equal to, pi over 6 over here plus 2 root 3 over 8, which evaluates to 2 pi over 3 plus root 3. Question number 61. We have the integral of square root of x squared plus 4x dx. Completing the square gives x plus 2 all squared minus 4. And now I can perform a trig substitution with x plus 2 being equal to 2 secant theta dx is equal to 2 secant theta tangent theta d theta, and this integral is equal to square root of 4 tan squared x times 2 secant theta tan theta d theta. This gives 2 times 2, which is 4, integral of tan squared theta secant theta d theta, and tan squared theta can be written as secant squared theta minus 1, which means this entire integral can be written as 4 times the integral of secant cubed theta minus secant theta d theta. And as seen previously in the previous question, the integral of secant cubed is 1 over 2 secant theta tangent theta plus 1 over 2 natural log absolute value of secant theta plus tangent theta minus the integral of secant theta is natural log absolute value secant theta plus tangent theta, and that is equal to 4 times 1/2 secant theta tangent theta minus 1/2 natural log absolute value secant theta plus tangent theta, which is equal to 2 secant theta tangent theta minus 2 natural log absolute value of secant theta plus tangent theta plus c. Oh, I forgot to substitute the x back into the equation. So we had 2 secant theta tangent theta minus 2 natural log absolute value of secant theta plus tangent theta, and the substitution we had taken was x plus 2 is equal to 2 secant theta. So now the triangle we have over here is theta x plus 2 over 2, and this is x squared minus x squared plus 4x, and therefore we have 2 secant theta, which is x plus 2 over 2, tangent theta, which is square root of x squared plus 4x over 2, minus 2 natural log absolute value of minus 2 times natural log absolute value of x plus 2 over 2 plus square root of x squared plus 4x over 2, and all of that simplifies to x plus 2 times square root of x squared plus 4x over 2 minus 2 natural log absolute value of x plus 2 plus square root of x squared plus 4x all over 2 plus c, and that is the answer in terms of x. Onwards to question number 62. Which is the integral x squared e to the x cubed. Integral of x squared times e to the x cubed dx. Now you can think about this. You can use substitution here, reversing the chain rule. You get 1/3 e to the x cubed plus c, because the derivative of e to the x cubed is e to the x cubed times 3x squared. You have the x squared, you're missing a third. So yeah. Question number 63. We have the integral of x cubed e to the x squared dx. We can use integration by parts for this, and we have the DI method over here, plus, minus, plus, minus, plus. We'll be differentiating x cubed and integrating e to the x squared. Differentiating x cubed, we have 3x squared, 6x, 6 and 0. Integrating e to the x squared, we have e to the x of we have to do it the other way around. With the DI method, I'll be integrating x cubed and I'll be differentiating e to the x squared. Integrating x cubed is x to the 1/4 x to the 4th. Differentiating e to the x squared is e to the x squared times 2x. Now, this integral therefore evaluates to x to the 4 over 4 times e to the x squared minus the integral of these two, the product of these two terms, which is which gives e to the x squared times x to the 5 dx over 2. I'm going to try that again. With the DI method, differentiate x cubed, integrate e to the x squared. No, I can't do that. I use a u substitution with let u equal e to the x squared, du is equal to 2x e to the x squared dx. Therefore, this integral is equal to x cubed times u, and dx is equal to du over 2x u. And now we have the integral 1/2 the u's cancel, and I have 1/2 the integral of x squared du, and that in terms of u is equal to 1/2 the integral of natural log of u du. That's because a natural log, because u is e to the x squared, and the natural log of e to the x squared will be x squared. And now I can integrate this by parts, and with the d I set up, I'll be integrating 1, differentiating natural log of u, and that gives me 1 over u, and that gives u, and therefore I have 1/2, this integral evaluates to 1/2 times u ln u minus the integral of du, which is 1 over 2. Substituting u back into here, we have e to the x squared. Natural log of e to the x squared is x squared. And minus 1/2 u, integral of du is u, and u is equal to e to the x squared, so minus 1/2 e to the x squared and plus c, and that's the answer to that question. Question number 64. This is the integral of tan x natural log of cosine x dx. So I'm going to perform a u substitution with u is equal to cosine x, du is equal to sine x dx, and now this integral is equal to, so tan x is equal to sine x over cosine x, so I have sine x over cosine x, natural log of cosine x dx. Now, as you can see, the dx and the sine x can be multiplied to give du, and now I'll make the substitution in the next line. So I have 1 over u, natural log of u du, and I can perform another use, and now you can just reverse the chain rule here, because 1 over u is the derivative of natural log of u, and therefore I have natural log of u whole squared over 2, and that is, substituting u back in, we get natural log of cosine of x whole squared over 2 plus c. Question number 65. This is the integral of 1 over x cubed minus 4x squared dx, which is equal to the integral of 1 over x squared times x minus 4 dx. Now, using this factorization, I can use partial fractions. So I have a over x minus 4 plus b over x, plus bx plus c over x squared dx. So using the terms, so using the value of x is equal to 4, using the value of x is equal to 4, x equals 4, I get the following values. I get 16a is equal to 1, So therefore I get the value that a is equal to 1 over 16. I then get the value for x's. Then I use the value of x is equal to 0 to get the equation minus 4c is equal to 1. So c is equal to minus 1 over 4. Now using the value of x is equal to 1, I get the following equation, which is 1 over 16 1 over 16 minus 3b and plus 3 over 4 is equal to 1. Therefore b minus 3b is equal to 3 over 16. Therefore b is equal to minus 1 over 16. And now using those values, I have 1 over 16a and I can then split up this bx plus c further into bx over x squared plus c over x squared, and remember that c was minus 1 over 4. Wait, was c minus 1 over 4? Yeah, c was minus 1 over 4, and therefore I can split up the integral as 1 over 16 integral of 1 over x minus 4 plus minus 1 over 16 integral of x over x squared, which is 1 over x, minus 1 over 4 the integral of 1 over x squared and dx and dx. Now following on from there, we have we can integrate the first integral as a natural log, so we have 1 over 16 natural log absolute value of x minus 4. The second one can also be written as a natural log 1 over 16 absolute value, natural log absolute value of x. And the final term can be written as minus 1 over 4 and that's x to the minus 2. Minus 2 plus 1 is minus 1, so x to the minus 1, and dividing by minus 1. And all of that gives, these two logarithm terms can be combined to give you 1 over 16 natural log absolute value of x minus 4 over x plus 1 over 4x plus c. And that is the answer. question 66. I have the integral of sine x cosine of 2x dx, and this is equal to the integral of sine x times cosine squared of x minus 1, and 1 is 1 is equal to sine squared plus cos squared. Yeah, so 2 cos squared, yeah, dx. So that's right, and then we have the integral of, so 2 times the integral of cos squared x sine sine of x dx minus the integral of sine of x dx, and here you can perform a u substitution using as the derivative of cosine is minus sine, so we have minus 2 cosine cubed of x, and dividing by the power is, so you have minus 2/3 cosine cubed of x, and the integral of minus sine of x is positive cosine of x, and that's plus c. That's the answer. And that is another page of questions done. We're 2/3 of the way through. Question 67. It's the integral of 2 natural log of x dx. So this can be written as the integral of e to the power of natural log of 2 e to the power of e to the power of natural log of 2 to the power of ln x dx, which is equal to the integral of e to the ln 2 times ln x dx. Therefore, integrating by parts, you have integrate 1, differentiate e to the ln 2 times ln x. The integral gives x, the derivative here gives e to the ln to ln x times multiplied by ln of 2 and then the derivative of ln x, which is 1 times 1 over x. And therefore, integrating by parts gives the following result, where x e to the ln to ln x minus the integral of e to the ln to ln x times ln 2 over x times x dx. Now, the x's cancel out. This integral can be this term can be simplified to x times 2 to the power ln x and this integral natural log of 2 is a constant, so that can be brought out of the integral, which leaves the integral of e to the ln 2 e to the ln 2 times ln x, which is 2 to the power ln x dx. Now if you notice this, you can see that this integral appears on the left hand side as well, so sending this over to the left hand side, we have 1 plus ln 2 times the integral 2 to the ln x dx is equal to x times 2 ln x. So the integral 2 to the ln x dx is equal to x times 2 ln x over 1 plus ln 2 plus c. And that is the answer. Continuing on to question number 68. The integral of square root of 1 plus cosine of 2x dx. This integral cosine of 2x is equal, this can be written as the integral of square root of 1 plus cos squared x minus sine squared x dx, which is equal to the integral of square root of 1 minus sine squared is cos squared, and cos squared plus cos squared is 2 cos squared x dx. So we have square root of 2 integral of cosine x dx, which is equal to square root of 2 sine x plus c. Question number 69. We have the integral of 1 over 1 plus tan x dx and this can be written as the integral of 1 over cosine x plus sine x over cosine x dx, which is equal to the integral of cosine x over cosine x plus sine x dx. And multiplying the Oh, how do I do this question? Oh, 1 is equal to secant squared x minus tan x. No, that doesn't help. Cosine squared x minus sine squared x, we get cosine of 2. Multiply the numerator and denominator by cosine x minus sine x. Gives you cosine squared x on the top minus cosine x sine of x all over cosine squared x minus sine squared x dx. No, that doesn't do anything. Let's try a u substitution, where u is equal to 1 plus tan x, du is equal to secant squared x dx. This is equal to integral of 1 over u. Dx is equal to du over secant squared x, and secant squared x is equal to secant squared x is equal to tan squared x plus 1, and tan squared x plus 1 is equal to u minus 1 squared plus 1. So I can rewrite that as 1 squared plus 1. No, the substitution doesn't work. Let's rewrite that as 1 plus tan x minus tan x 1 plus tan x minus tan x minus 1 dx plus 1, no. Okay. So all of this is equal to, everything in the numerator is equal to 2, and therefore if I do a half, these two expressions are equivalent. This allows me to split up this integral as 1/2 times 1 dx minus a half integral of plus an integral of plus the half integral 1 minus tan x plus tan x dx, and we have already evaluated this integral before because this is equal to because this integral is equal to cosine x minus sine x over sine x plus cosine x, which is and the integral of this is equal to the natural log of the denominator here. So evaluating this gives x over 2 plus 1/2 integral of this previous integral, which is equal to natural log absolute value of cosine x plus sine x plus c, and that is the answer. Next we have question number 70, which is the integral of from 1 over e to e of square root of 1 minus natural log of x squared over x dx. You can perform a u substitution over here with u being equal to natural log of x. This is equal to the integral of x is equal to making the substitution, when x is equal to 1 over e, we have ln over x equal to minus 1, and ln of and when x is equal to e, we have natural log of e being equal to 1, and this therefore gives square root of 1 minus u squared du. And now we can make another sub here such that u is equal to sine theta, du is equal to cosine theta d theta, and when u is equal to -1, theta is equal to minus pi over 2. When u is equal to 1, theta is equal to pi over 2. And we have square root of 1 minus sine squared, which is cosine, square root of cosine squared, which is cosine theta. Du is equal to cosine theta d theta. And this is the, now we can evaluate this using the power reduction formula for cosine. And this is equal to 1x over 2, theta over 2 plus sine of 2 theta over 4 between pi over 2 and minus pi over 2. And this evaluates to pi over 4 plus sine of pi, which is 0, minus of minus pi over 4, so minus of minus pi over 4, minus sine of minus pi, which is 0, which is equal to pi over 2. Question 71 71 is the integral of 1 over cube root of x plus 1 dx, and perform a u substitution with u is equal to cube root of x plus 1, du is equal to 1/3 of x, and 1/3 minus 1 is minus 2/3, is x to the minus 2/3 dx, and substituting that back in, we have integral of 1 over u, and dx is equal to 3 du over x to the minus 2/3, which is equal to 3 times the integral of cube root of x squared over u du, and that in terms of u is u plus 1 squared over u du, and this can be easily evaluated using the power rule. We have then the integral of u squared over u, which is u, plus 2u over u, which is plus 2, plus u to the minus 1 du, and all of this is equal to 3 over 2 u squared, and u is that, so we have cube root of x plus 1 squared, plus 2u, plus 3 times 2u, which is 6u, we have plus 6 cube root of x plus 1, and we have natural log, plus 3 times natural log of u, so we have plus 3 natural log absolute value of cube root of x plus 1, and plus c, don't forget the plus c, and that's the answer to that. Next up we have question number 72. this is the integral of 1 over cube root of x plus 1 entire cube root dx. You can just perform a u substitution with u equal to x plus 1, du is equal to dx, and that is equal to the integral of u to the minus 1/3 du, and minus 1/3 plus 1 is 2/3, and dividing by 2/3 is 3 over 2, u to the power 2/3, which is x plus 1 to the power of 2/3 plus c, and that's the answer for that. Now we have question 73. This is the integral of sine x plus cosine x all squared dx. This is equal to the integral of sine squared x plus cos squared x plus 2 sine x cosine x dx, and sine squared plus cos squared is 1. So all of this right here is equal to the integral of 1 plus sine of 2x dx, and therefore integrating that gives x plus x minus cosine of 2x, and reversing the chain rule, over 2 plus c, and that is the answer right there. That's question 73 done. So that was question number 73. Next up we have question number 74. This is the integral of 2x natural log of 1 plus x dx, and to integrate this I will be performing not a u substitution, I'll just be going with integration by parts. Differentiate natural log of 1 plus x, integrate 2x. Integral of 2x is x squared. Derivative of ln of 1 plus x is 1 over 1 plus x. Is that okay, or can I do something else? If 1 plus x, I have 2 times u minus 1. No, there isn't an answer that directly jumps out, so I'm not going to do that. Instead, I'll try a u substitution with 1 plus x is equal to u, dx is equal to du, and I have an integral of 2 times u minus 1 natural log of u to u, and now I have, which is equal to 2 times the integral of u ln u minus 2 times the integral of ln u up du on both places. Yeah, now I can integrate both of these by parts. So integrating the first expression by parts, I have differentiate natural log of u, integrate u. Integrating u gives me u squared over 2, derivative is 1 over u, and I can stop right there. For this expression, I have integrate 1 to x, integrate 1 to u, to differentiate natural log of u to 1 over u, and differentiate natural log of u to 1 over u, and applying integration by parts gives me 2 u squared over 2 natural log of u minus the integral of minus 2 times the integral of u over 2 du, and that's the first expression. And with the second expression we have a minus 2 u ln u, and a minus 2 times minus, so that's a plus 2 integral of du, and all of that is equal to u squared ln u, right there, minus integral of u, which is minus u squared over 2 minus 2u ln u plus 2u, and finally just substitute x back into the answer to get x plus 1 squared, natural log of x plus 1 minus x plus 1 squared over 2 minus 2 times x plus 1 natural log of x plus 1 plus 2 times x plus 1 plus c, and that is the answer right there. Moving on to question number 75, 3/4 of the way through, almost there. I have an integral of 1 over x times 1 plus sine squared of ln x dx. You can perform a u substitution here because ln x and with u equal to ln x, and you have du is equal to 1 over x dx, so this just becomes 1 over 1 plus sine squared u du. 1 plus sine squared u is cos squared u, and therefore this entire integral is secant squared u, which du, which integrates to tangent of u plus c, which is tangent of natural log of x plus c. And that's the answer. Number 76. Integral of square root of 1 minus x over 1 plus x dx. If I let Oh yes, u is equal to 1 plus x, du is equal to dx, and this integral becomes square root of u. So this is x is equal to u minus 1. So I think this is 2 minus u. Does that work? 2 minus 1 minus x. Yeah, so over u du. So this is the integral in terms of u. And this allows me to split it up into the integral of oh wait, what can I do with this? What can I do here? Oh wait, I know what to do. Is it just using long division, maybe? Differentiate, long division with 1, so minus x plus 1, and with respect to x plus 1, have a minus 1, and I need a minus of minus x, and I get 0 and plus 2. But I can't split up the fraction, which is the problem. Multiply numerator and denominator by... Okay, fine. This is equal to integral of square root of 1 minus x over square root of 1 plus x. Multiply both numerator and denominator by square root of 1 minus x. No, it doesn't change anything. By square root of 1 plus x, yes. Dx. And that is equal to the integral of square root of 1 minus 1 minus x squared over 1 plus x dx. Now I can do this. I think I'll multiply numerator and denominator by 1 minus x squared. Sorry, square root of 1 minus x. And that will be equal to the integral of 1 minus x squared in the square root of 1 minus x squared in the denominator, and 1 minus x in the numerator dx that is it. Then I can split up this fraction as integral of 1 over 1 minus x squared dx minus the integral of over square root of 1 minus squared dx. Now here, this integrates to sine inverse of x. Over here, I can perform u substitution with u being equal to 1 minus x squared du is equal to minus 2x dx, and therefore this integral becomes x over square root of u, and I have dx is equal to du over minus 2x, and the minus minus becomes plus, and these two x's cancel out, and this gives me the answer of sine inverse of x, plus 1/2, and then u to the minus 1/2 to the power 1, sorry, minus 1/2 plus 1 is 1/2, dividing by 1/2 is multiplying by 2, and u to the 1/2, so 1 minus x squared to the power, so square root of 1 minus x squared. So I get square root plus c, and just simplifying that up a bit, the 2 and the 1 over 2 cancel out, and that is the answer. That was question number 76. Almost there. So that was question 76, 77. Integral of x to the x over ln x dx. And how do we do that? So this can be written as e to the natural log of x to the x over ln x dx, and using the property of logarithms, we have natural log of x times x over ln x dx, and this is equal to e to the x, which is equal to e to the x plus c, and that is done. 78. We have the integral of sine inverse square root of x dx. Performing a u substitution and integration by parts. So substitution first. U is equal to square root of x 2u du is equal to dx. 2u du is equal to dx, which we have sine inverse of u is equal to, so times 2u du, and now we can integrate by parts. Differentiating sine inverse of u, integrating to u we have u squared, differentiating sine inverse of u we have 1 over square root of 1 minus u squared. I think that's right. Yes, that is right. And so this gives u squared sine inverse of u minus integral of u squared du over 1 minus u squared, square root of 1 minus u squared. And so I just need u. Oh wait, instead of doing this, I'll do it without the u substitution. Directly integration by parts. Integrate 1 to get x, differentiate sine inverse of square root of x to get 1 over square root of 1 minus, it has to be square root of x squared, which is just x. Now I get x sine inverse of square root of x minus the integral of x over square root of 1 minus x dx. Now I could perform substitution. I don't know if I need to. Oh, okay. Use a u substitution with 1 minus x is equal to u, dx is equal to minus du. So then we have this integral being equal to x sine inverse of square root of x minus this integral, we have an integral of 1 minus u over square root of u, and we have a minus du, and this ends up becoming x sine inverse of square root of x plus, so the integral of 1 over square root of u is 2 square root of u, and we also have, so this minus and this minus have become a plus, yes, and so then we have a minus integral of square root of u and u to the half. Integrating that gives u to the 3 over 2 and 2/3. And we can substitute x back into this equation to get x sine inverse of square root of x plus 2 square root of 1 minus x minus 2/3 square root of 1 minus x to the power of 3 over 2, and don't forget the plus c. And that is the answer. Question 79. I have the integral of tan inverse of x dx. Integrate this by parts. Integrate 1 to get x. Differentiate tan inverse of x to get 1 over 1 plus x squared, and this gives x tan inverse of x minus the integral of x over 1 plus x squared dx. Performing a u substitution where u is equal to x squared plus 1, you see that du is equal to 2x dx, and therefore you have x tan inverse of x minus 1/2 natural log absolute value of 1 plus x squared. And x squared is always positive, so there is no need to have an absolute value sign around 1 plus x squared. And don't forget the plus c, and that is the answer. Question 80. Integral from 0 to 5 of f of x dx, where f of x is equal to 10 if x is less than or equal to 2, and 3x squared minus 2 if x is greater than 2. So therefore we can split up this integral as integral from 0 to 2 of 10 dx plus integral from 2 to 5 of 3x squared minus 2 dx, and that is equal to 10x evaluated from 2 to 0 plus x cubed minus 2x valued from 5 to 2, and that is equal to 20 minus 0 plus 125 minus 10 minus 8 minus plus 4, and all of that is equal to 45, 131. Question number 81. The integral of sine of 1 over x over x cubed dx. We have 1 over x is equal to u, and differentiating both sides, we have d x to the minus 1, so we have minus so that is correct. And now substituting this, we have an integral of sine of u. Dx is equal to d over x cubed, sine u over x cubed. Dx is equal to du times x squared over minus 1. So we can see that all of this simplifies to the negative integral of sine of u over x du, and 1 over x is the same as u, so this can be rewritten as u sine u du, integrating by parts with the di setup. Differentiate u, integrate sine of u, and since we have a minus, let's just include that minus with the minus sign. So differentiating u gives 1 and then again gives 0. Integrating negative sine gives cosine. Integrating cosine gives positive sine. And therefore the final answer is u cosine u minus sine of u plus c. And now you can substitute x back in. So u is equal to 1 over x. So 1 over x cosine of 1 over x is equal to minus sine of 1 over x plus c. And that is the answer. Come on, 19 more to go. Almost there. Question number 82. This is the integral from x minus 1 over x to the 4 minus 1 dx. Integral of x minus 1 over x to the 4 minus 1. And this is equal to the integral of x minus 1 over x squared plus 1 times x plus 1 times x minus 1 dx, and all of that simplifies the integral down to 1 over x squared plus 1 times x plus 1 dx. And now I can do partial fractions on that. So integrating this, we have a x plus 1, a over x plus 1, plus bx plus c over x squared plus 1 dx. Now, let's set x is equal to minus 1. We get that a is equal to 1 over 2. Yes, setting x is equal to 0, we get that a plus c is equal to 1, therefore c is also equal to 1 over 2. And setting x is equal to plus 1, we get 2a, so we have 2 times 1/2, which is just 1, so 2a, which is 1, plus 2b plus to c, which is also 1, and all of that has to equal 1. So we know that b is equal to minus 1 over 2. And all of this can be put down on here. And this then allows me to split up the polynomial like 1 over 2 as follows, which is 1 over 2 integral of 1 over x plus 1 dx plus minus 1 over 2 integral of x minus 1 over x squared plus 1 dx. And this indeed can be split up further into x dx, and there was a minus 1, so that's plus 1 half integral of 1 over x squared plus 1 dx. And now we have 1 over 2 natural log absolute value of x plus 1, and you can use a u substitution here, and we have minus 1 over 4 natural log absolute value of x squared plus 1 and then we also have plus 1 over 2 arctan of x plus c, and that is the answer. Question number 83. Integral of square root of 1 plus x minus 1 over 4x all squared dx. So this can be rewritten as integral of square root of 1 plus 4x squared. So we have 4x squared minus 1 over 4x all squared dx. Which is equal to the integral of square root 16x squared plus 4x squared is 16x to the 4th minus 8x squared plus 1 over 16x squared and continuing the working from there, we have the integral over 4x dx of square root of 16x squared, 16x to the 4 plus 8x squared plus 1, and that as you've probably noticed, is square root of 4x squared plus 1 all squared over 4x dx, which is equal to the integral of 4x squared plus 1 over 4x dx, which is equal to the integral of x plus 1 over 4x dx, which is equal to x squared over 2 plus 1 over 4 natural log absolute value of x plus c, and that is the answer. Still going strong, come on. Question number 84. Integral of e to the tan x over 1 minus sine squared x dx. You can see that 1 minus sine squared x is equal to cosine squared x. 1 over cosine squared is secant squared. So this is the integral of e to the tan x secant squared x dx, and therefore by inspection we have this is the integral of e to the tan x plus c, reversing the chain rule. Question number 85. This is the integral of tan inverse of x over x squared dx, and we can use integration by parts. So with the di method, I'll be integrating x to the minus 2, differentiating tan inverse of x. The derivative of inverse tangent of x is 1 over 1 plus x squared, and the integral of x to the minus 2 is x to the minus 1, and we have minus 1 over x. Continuing this, how do we go from here? Okay, so I have a minus tan inverse of x over x plus an integral of 1 over x times 1 plus x squared dx, and here again you can use partial fractions, and you can have a over x plus bx plus c over x squared plus 1 dx. By setting x is equal to 0, we find that a is equal to 1. By setting x is equal to 1, we have 2 plus b plus c is equal to 1, and by setting x is equal to minus 1, we can have 2 minus 2 plus b minus c is equal to 1. From those steps we have that, using those two equations, we get that 4 plus 2b is equal to 2, b is equal to 0, and therefore c is equal to minus 1. No, sorry. 2 plus, so 4 plus 2b is equal to 2, b is equal to 0, okay. Therefore we have c is equal to no, something isn't right. At x equals 0, I get a is equal to 1, okay. At x is equal to 1, I get b plus c, 2 plus b plus c is equal to 1. At x is equal to minus 1, I get c minus b. I get c plus b. Oh, sorry. B minus c plus 2 is equal to 1. Okay. And so since b is equal to 0, c is equal to... Oh wait, no, something has gone wrong here. Let's say x is equal to 2. At x is equal to 2, I get 3 plus 4b plus 2c is equal to 1. Okay, so now b plus c is minus 1 half. 3 plus so I do get b is equal to 0, and I get c is equal to minus 1. Yes, c is equal to minus 1. Yeah, so those are the values obtained after doing partial fractions. This then allows me to evaluate the integral as follows, which is minus tan inverse of x over x plus natural log absolute value of x minus the integral of 1 over 1 plus x squared dx, which is the arctangent, so minus arctan, so tan inverse of x plus c, and that is the answer. Oh, 86. This is an easy one. We have integral of tan inverse of x over 1 plus x squared dx, and you can identify that 1 over 1 plus x squared is the derivative of tan inverse, so reversing the chain rule we have 1 over 2 and tan inverse of x squared plus c, and that is the answer. 87. So 87 is the integral of natural log of x all squared dx. So we know from previously in the video that the integral of natural log of x is equal to x ln x minus x, and therefore applying integration by parts to here, differentiating natural log of x and integrating natural log of x, we have 1 over x, and integrating we get x ln x minus x, and therefore we can rewrite this integral as the integral as x ln x minus x times natural log of x minus the integral of ln x minus 1 dx, and we already have the answer to that. So this is x ln x minus x times ln of x. Integral of ln of x from here we know is so negative x ln x plus x, and minus minus is plus, so we have another plus x plus c. And can this be simplified further? Yes, so you can simplify this further down into x ln of x squared minus 2x ln x plus 2x plus c, and that is the answer. That's another page, and now we're on to the final page. Yes! Question number 88. The integral of square root of x squared plus 4 over x squared dx. You can do this by u substitution, or even by if you substitute I'll try doing this way with trig sub. X is equal to 2 tan theta, and we have dx is equal to 2 secant squared theta d theta. Therefore this entire integral here is equal to 4 tan squared theta plus 4 is 4 sec squared theta, and we have 4 tan squared theta, and this is 2 sec theta d theta. This over here is equal to the 2 times 2 over 4 cancel out, so you have secant cubed theta over tan squared theta d theta. You can rewrite this as integral of secant squared theta, tan squared theta plus 1 times secant theta over tan squared theta d theta. That is indeed equal to distributing the secant and dividing by tan squared, we have integral of secant theta plus d theta plus the integral of secant theta over tan squared theta d theta. We know the value for this is natural log absolute value of secant theta plus tangent theta, and this can be written as cosine squared theta over sine squared theta times 1 over cosine theta d theta, and the cosine and the square cancel out. Now you can perform a simple u substitution where u is equal to sine theta, and you are left with the integral of 1 over u squared, which is minus 1 over sine theta and plus c, and that is the answer. '89. Integral of square root of x plus 4 over x dx. So to do this question, I think I'll use trig sub again. So x is equal to x is equal to 4. Oh, you need to substitute. I forgot to substitute x back in here. So if you wanted to make that substitution, you'd have natural log absolute value of so you'll have secant theta, which is square root of x squared plus 4 over 2, plus x all over 2 minus 1 over sine theta, which is square root of x squared plus 4 over x plus c, and yes, that is your final answer. For tan squared theta, dx is equal to 8 tan theta secant squared theta d theta, and all of this is equal to the integral from square root of 4 secant squared theta 8 tan theta d theta all over 4 tan squared theta. So as you can see, the tan theta and the square cancel out. The square root of 4 is 2, 2 times 8, 16 over 4 is 4. Integral of secant theta times secant, which is secant cubed theta over tan theta d theta. And this is equal to 4 times the integral of secant squared tan squared theta plus 1 times secant theta d theta over tan theta. That is all equal to 4. Integral of tan theta secant theta plus the cosine theta over sine theta times 1 over cosine theta d theta. This is equal to 4 secant theta plus 4 times the integral of 1 over sine theta d theta. And here I'm going to use the so this is equal to the integral of cosecant theta, and which, as shown previously in the video, you can obtain by multiplying and numerator and denominator by cotangent theta minus cosecant theta, and you should have cotangent theta minus cosecant theta, and therefore you should have 4 natural log absolute value of cotangent theta minus cosecant theta plus c. Now substituting our values back into this equation, we had theta, so we had tan theta equal to square root of x over 2, and therefore tan squared theta was x over 4. Yes, that is correct. And so now here we have the square root of x plus 4. Now substituting our values back in, we have 4 times secant theta, which is square root of x plus 4 over 2, which gives 2, plus 4 natural log absolute value cotangent is 2 over square root of x minus cosecant, which is square root of x plus 4 all over, so square root of x, and we have a plus c, and that is our final answer right there. We have question number 90, which is the integral from 0 to pi over 2 of sine cubed x over sine cubed x plus cosine cubed x dx. Now let's call this integral equivalent to I. Now, we need to, let's consider another integral of 0 to pi over 2 of cosine cubed of x over cosine cubed of x plus sine cubed of x dx. And let's call this j. Now, now for j, let's consider for the integral j, let's consider the substitution u is x is equal to pi over 2 minus u. Now make dx is equal to minus du. This means that j is equal to the integral from, so when x is equal to 0, u is equal to pi over 2. When x is equal to pi over 2, u is equal to 0. So integral from pi over 2 to 0 of cosine cubed of pi over 2 minus u over cosine cubed of pi over 2 minus u plus sine cubed of pi over 2 minus u, and we have dx is equal to minus du. Now, since this is the case, we can, since we have a negative, we can swap the limits at the expense of the negative sign and have 0 to pi over 2. And now we can show that cosine and sine are functions that differ by pi over 2, and they have a pi over 2 shift. Therefore, this is identical to sine cubed of u, sine cubed of u over cosine over sine cubed of u plus cosine cubed of u du, and therefore j is equivalent to I. Now that we have shown that j is equivalent to I plus j is equal to 2I, which is equal to the integral from 0 to pi over 2 of sine cubed x over sine cubed x plus cos cubed x plus dx, plus cos cubed x over sine cubed x plus cos cubed x dx. So this is 2i is equivalent to this function. Therefore 2i is equal to the integral from 0 to pi over 2 of 1 dx, which is equal to pi over 2. And since 2i is equal to pi over 2, I is equal to pi over 4, giving the answer to integral from 0 to pi over 2 of sine cubed of x over sine cubed of x plus cosine cubed of x dx is equal to pi over 4. And that is the answer. We're almost there. Come on. 91. We have the integral of x over 1 plus x to the 4 dx. Let u equal to 1 plus x to the 4, du is equal to 4x cubed dx. So this integral is equal to x over u, and dx is equal to du over 4x cubed, which means x squared. No, this isn't useful. We can rewrite this as x over 1 plus x squared all squared dx. Now performing a u substitution for u is equal to x squared, du is equal to 2x dx. We have an integral of 1 over 2 du over 1 plus u squared, and this is equal to 1 over 2 arctan of u plus c, which is equal to 1 over 2 arctangent of x squared plus c, and that is the answer. 92. Integral of e to the x over 2, e to the x to the 1 half dx. Therefore this integral is equal to e to the u and times 2u du. Now integrating by parts. Integrating e to the u, differentiating 2u, we have 2 and 0, e to the u and e to the u, and this is therefore equal to 2u e to the u minus 2 e to the u plus c, and that is the answer. 93. integral of 1 over cosecant cubed of x, which is the same as the integral of sine cubed of x dx, which is equal to the integral of 1 minus cosine squared x times sine of x dx, and this is equal to cosine cubed of x over 3 minus and you can get this result by using u substitution, with u is equal to cosine x. We now have an integral of sine inverse of x over square root of 1 minus x squared dx. Using a u substitution of u is equal to sine inverse of x, we get that this integral is equal to u du, which is equal to u squared over 2 plus c, which is 1 over 2 sine inverse of x all squared plus c, and that is the answer. 95 over here is equal to the integral of so 95 is the integral of square root of 1 plus sine of 2x dx, and this is the same as so yes, this is equal to square root of, I'll rewrite it down here. So this is equal to the integral of square root of sine squared of x plus cosine squared of x plus 2 sine x cosine x dx, which means this is the integral of sine x plus cosine x, because this expression is sine x plus cosine x squared, and square root is just sine x plus cosine x, and dx, and the integral of this is equal to sine x minus cosine x plus c, and that is the answer. 6 more questions to go, come on. Question number 96. Integral of x to the 1 over 4 dx, and this is equal to 4/5 x to the 5 over 4 plus c, and that is the answer. 97. We have the integral of 1 over 1 plus e to the x dx. Okay. U is equal to 1 plus e to the x du is equal to e to the x dx, and this integral is equal to 1 over u, and dx is equal to du over u minus 1. Okay, no, wait, hang on. No, I think there has to be. Oh, sorry. This is equal to integral of 1 plus e to the x minus e to the x over 1 plus e to the x dx. This is equal to the integral of 1 dx minus the integral of e to the x over 1 plus e to the x dx. Now this is just equal to x, and here we have a negative. Using u is equal to 1 plus e to the x, du is equal to e to the x dx, and we have minus natural log of absolute value 1 plus e to the x and plus c, and that is the answer here. That was 97. We have 98. Square root of 1 plus e to the x dx. Let u equals 1 plus e to the x. Du is equal to e to the x dx. This means that this integral is equal to square root of u. Dx is equal to du over u minus 1. And this can therefore be written as I think I'll just use a trig sub here. E to the x is equal to tan squared x. We have this integral being equal to, tan squared theta. E to the x dx is equal to 2 tan theta secant squared theta d theta, and this integral is therefore secant theta times 2 tan theta secant squared theta d theta all over e to the x, which is tan squared theta, and these two cancel out, and we get an integral of 2 integral of tan squared theta plus 1 times secant theta d theta over over tan theta, and this is equal to 2 times tan squared theta. We have 2 integral of tan theta secant theta plus 1 over tan theta times secant theta, which is cosine theta over sine theta. Is that right? Oh, sorry, 1 over sine theta. Yes, 1 over sine theta, and this is equal to 2 times secant theta plus 2 times the integral of cosecant theta, and we already know the integral of cosecant theta, which is plus 2 times natural log absolute value of cotangent theta minus cosecant theta. And now substituting the values back in, we had theta. We had tan theta is equal to square root of e to the x. So we have the hypotenuse being e to the x plus 1, and therefore secant theta is 2 square root of e to the x plus 1 plus 2 natural log cotangent is adjacent over, so we have 1 over square root of e to the x minus square root of e to the x plus 1 over square root of e to the x, and plus c. And that is the answer to that. Last few questions remaining. Okay, so we have question number 99. Integral of square root tan x over sine of 2x dx. U is equal to square root of tan x. So now we have u squared is equal to tan x, 2u du is equal to secant squared x dx. And this is equal to the integral of u over 2 sine x cosine x, and dx is equal to 2u du over secant squared x. We get an integral of u squared du over sine x times cosine x over 1 over cosine squared x. And right here we have all of this, all of this right here is equal to tan x. So we have an integral of u squared du over tan x, which is u squared, and that is equal to u, which is square root of tan x plus c. That's question 99. Question number 100. We have the integral from 0 to pi over 2 of 1 over 1 plus sine of x dx. This is equal to the integral from 0 to pi over 2. And multiply the numerator and denominator by 1 minus sine squared, so 1 minus sine x over 1 minus sine squared x, which is equal dx, which is equal to the integral from 0 to pi over 2 of 1 minus sine x over cosine squared x dx, which is equal to the integral of 0 to pi over 2 of secant squared x minus secant x tangent x dx. And now these are regular standard integrals, and therefore we have to evaluate these. So we have tan x minus secant x from pi over 2 to 0. Now these can be rewritten as sine x minus 1 over cosine x, and we can multiply that by sine of x plus, sine x plus 1 from 0 to pi over 2, and we have oh no, hang on, I think it's So I don't want a cosine at the bottom. So go for so then this gives me sine squared x minus 1, which is minus sine squared x minus 1. 1 minus sine squared is cos squared, so this is minus cos squared x over cosine x times sine x plus 1 from pi over 2 to 0. And the squared and cosine x cancel out, and now we can sub in these values, and that gives me so cosine of pi over 2 0 minus so 0 over 2, and then we have a minus of minus cosine of 0 is 1 and sine of 0 is 0, but we have a plus 1 there, and therefore this final answer is plus 1. Now for the final integral. Now the final integral, integral number 101, the integral of sine of x over x plus natural log of x times cosine of x dx. And quite naturally, just by inspection you can see that 1 over x is the derivative of natural log of x, and cosine of x is the derivative of sine of x, and therefore we can undo the product rule, and by inspection we have that this is equal to sine of x natural log of x plus c, and then we're done. So thank you for watching the video. Thank you to Blackpenredpen. He gave me the motivation to do this. If you haven't already, go subscribe to his channel. Please let me know if I made any mistakes in the comments down below, and thank you for watching.